pump thing, which is really an air conditioner running backwards, is a big deal. And we've got, in my view, one of the foremost experts to explain this. And he has taught me stuff by speaking slowly and using short words so I can understand. So please give an insane welcome for Bruce Harley.
Am I on? Good, thank you, Joe. I was kind of sick last week and my voice is a bit shaky, so I apologize. I will try to stick to short words. I'll try to include a little bit of humor, but I think the problem is, actually we could use this, right? Engineers and humor. If we wanted to really nail desiccant dehumidification, get a bunch of engineers in a box to tell jokes. Right? That's the style that I've got. It just gets worse from there, right? So after yesterday afternoon, I decided to ask the AI assistant on the BSc website, not a limerick about Joe, but a limerick about Stiebrick. And it was interesting because how do you rhyme Stiebrick, right? Well, the answer is you don't. You rhyme Stiebur. So the AI is no better at pronouncing your name, Joe, than you are. Your building science was sure. It rhymes with Stibur. On vapors and capers, was that the stuff that they put on smoked salmon, the little green things? Making buildings safe, sound, and secure. Well, that's good. I tried it with Straub, and he rhymes with probe. What exactly is that about? I guess he's probing into building science. Right. He's doing the same stuff, guides and papers, vapors and capers, and making buildings safe, sound, and snub, which is also kind of interesting. I'm not sure how you get a building to do this. But actually, the best one, and I apologize I didn't get this on the slide, there once was an architect named Betsy whose designs were always quite zesty. It's just a little reversal of the S and the T. She built homes with care, with energy to spare, making each one a cozy nesty. All right. It's being recorded, isn't it? Okay. So I'm going to talk a little bit about heat pumps, a little bit of history and context for heat pumps, and my experience throughout my career has been almost entirely with residential houses, residential systems, residential building science. We're going to look at test and rating systems that are done conventionally on heat pumps. And then we're going to look a bit at load-based testing and some of the work that I've been doing over the last 10 years, including we've recently completed or actually are almost completed with, and some ideas about where to go from there. And a few tips to stay out of trouble. That's actually just one slide at the end, a couple of slides, but hopefully it all ties in. But I'm going to start, I was actually really happy that Kent did a little bit of a personal intro, because last year everybody, is this my imagination, did everybody start with this personal story? And so far this year nobody had done that, so thank you to Kent for opening the door there. I have a few numbers about my experience of summer camp. Some of these are engineering numbers, they're rounded a little bit, but most of them are actually right on. This is me. I had my 60th birthday this year. 34 of those years, thank you. 34 years since I've been involved in residential energy efficiency and construction and things related to that. So well over half my life. The last almost 10 years of that has been as an independent consultant. This is my 20th time at summer camp. Started in 2002, and I've only missed 1 year. It's about 10 miles from the house where I grew up. And so I used to stay with my parents and then with my mother. And the last time I saw my mother alive was the very last day of summer camp in 2019, when I said goodbye to her to come here and then headed home. And she passed away just a few weeks later, and I missed seeing her again. So it's close to home. It's 10 years since I presented at camp. I talked about the heat pumps in my house in 2014, and about 5 years ago, I started bugging Joe, can I share some of the stuff that we've been learning? And he's, no, I have other stuff I want to have people talk about at camp. So 2 years ago, I asked him, he said, okay, you can get on the program. And when the program came out, when the agenda came out last year, I wasn't there. And I said, Joe, what's up? He said, I forgot. And actually, it turns out it's a really good thing. I was very happy because I don't say I've learned a lot more since then, but a lot of the work that we were doing that I thought I would be able to start sharing about roughly a year ago was not in any kind of shape to share, and it is now. So that's nice. It actually worked out really well that way. This is the 5th year that I played in the band in person. There were 2 years when we did a bunch of music videos, so look up on YouTube, Building Science Boogie Band. We did some really fun stuff. And made music videos. That was something that kept me and most of us sane for the last, during that difficult time. And the band has been great. It's like, this is a great community, and that is a great little micro community within the community, and I love playing with these guys. I bought my 5th electric guitar for my 60th birthday, which you can see if you come tonight to the clubhouse. And this is my very first time to really quite publicly declare my appreciation for Betsy and Joe, 10 to the 6th. A million thanks, yep. So yesterday, my daughter sent me a couple of pictures of me in 1994. Took completely apropos to nothing. She just ran across these and thought it was funny. I met Joe in 1994 at the Affordable Comfort Conference in Philly, and I still have the t-shirt to prove that I was there. And I thought he had some really cool stuff to say. The funny thing, when my daughter sent me this picture, she said, "You look like me." She's never seen me without a beard. That's her this year. And I'm just going to give a very, very flash-forward slideshow. In 2020, she was 15, and COVID happened, and we had talked about building a tree house or something, and it never happened for years. And so I said, all right, we're going to build a little guest cabin, a tiny house cabin in our backwoods. It's about 350 feet behind our house in the woods. And it was a blast. It was a fun project. She mixed cement. She did everything. This picture on the left, all right, we live in the woods. We live in the freaking, at the edge of the Green Mountain National Forest, and there's nothing but woods for miles around. And if anyone's ever built structures there, which I've built a few around my house, mice. Mice are a big problem. My office, which is the first little cabin I built, is in the summer, it gets kind of smelly, and it's embarrassing. I don't bring anyone there. So we built this structure. It is covered 100% with galvanized metal screening, including on the bottom of the floor. So we built the floor, and we put the screening and then plywood, and then we turned it upside down with a big block and tackle so that it's continuous even across the beams that hold it up. Thank you, Mark. And the screening on the right, you can see the screening goes over the XPS, right? We could have put just peel and stick under the XPS, but the mice love tunneling in XPS. Ask me how I know. My other cabin. And ants also love that stuff. So you can keep the ants out with borate treatments, but that doesn't help with mice. She did everything all the way up to nailing the floor down. We used a bunch of scrap wood that came from my parents' house that I also cleaned out that same summer. Furniture from my grandmother's apartment. And I found brass, is it brass or copper? I guess it's brass V-seal with a sticky back that was no longer sticky that had been in my parents' basement for 60 years and never used in the original package. And I figured out how to cut it for a round top door that I made out of African mahogany that was cut on the sawmill my grandfather built in West Africa in the 1930s. And that's the interior. So, some of the stuff that Joe taught all of us, this is, normal stuff that we've all heard many times: drain the rain on the plane, if you want to save cash, flash. Controlling the air, you must first contain the air. Kent actually talked about that just a couple hours ago. Don't do stupid stuff. One of the ones that I forgot to put on here is all windows leak, just like all buildings leak. Don't forget all windows leak. And one that was relatively recent was dense packed cellulose doesn't work in cold climates. And just last week, we had a new roof put on our house. I had a 20-year slab of petroleum that I built back in '94 when we built the house, and it went for 30 years and didn't leak, but I finally bought a new roof, which is an interlocking metal roof. And when they took off the old roof, you can see there to the right of the skylight, there's a band of dark and kind of nasty looking plywood. I originally made this, so below that is a little knee wall attic, and above that is a vented, upper attic. When I first built the house, I did 12 inches of fiberglass. I sealed everything as carefully as I could from the inside with polyethylene. I was kind of green at this stuff at the time, 1994, and it didn't work. I could see the frost melt right over the insulated part and not over the vented attics. So later I went back and I dense packed it with cellulose right up to the sheathing. And it stopped melting. That worked. But this is July, this is the end of July, and it was still damp from last winter. And I have had ice dam problems that formed occasionally at that interface where there was peel and stick along the bottom edge, but I didn't put it at the interface between that sloped ceiling and the lower vented attic below. And I had several winters where I had some serious ice dams and they were leaking back into the second story. So that's something that Joe and others have said over the years, and it's absolutely true. And that was a real fortune cookie that I got a couple of years ago. So it was about a little over 20 years ago, I was doing a little consulting for an institution in Worcester, Massachusetts, and they had some big buildings that they wanted to insulate, and I was suggesting closed-cell spray foam on the roof. And I had some wacky ideas about how do you deal with what happens when there's a leak in the roof above it. And I didn't know about IR inspections, infrared inspections, to look for wet foam, and I had come up with ideas, but I called Joe and I said, does this make sense? I'm not going to tell you what the idea was. It was stupid. And he said, no, and he told me about they should just write it in the plan every 5 years to do an inspection with an infrared camera to make sure that, you can identify where the leaks are. And the thing that he said to me then was, he said, Bruce, you have to be careful what you say. You're a thought leader. And I was like, what? Me? Little me? He said, people pay attention to stuff you say. This was actually before my first book got published. And if you're not careful what you say, you're going to, steer people the wrong way. And so after that, I started to be really, really careful about what I said. And you know what? It doesn't fucking work. I've done so many presentations where I talk about the point that I want to make, and I talk about the limitations around it. Like, here are the boundaries of where what I'm saying matters, and beyond that, don't, and people only take the big takeaway. I don't know why, we are so bad at sort of parsing out those subtleties and those provisos, you know, but it's some of the stuff that Kent was talking about earlier is related to that. And, you know, so I've just kind of given up, all right? So there's going to be a quiz at the end. Nobody gets your cookie and your coffee until you pass the quiz. All right. So heat pumps, you know, actually before I talk about what people say about heat pumps, I'm just going to say a couple things. Why is this important? What are heat pumps? Joe already explained a heat pump. It's an air conditioner that you took out of the window and you turned it around, so it's air conditioning the outdoors and heating indoors. You don't want to do that in the summer. But your refrigerator, your freezer, your air conditioner, they all, like, you know, air conditioners don't create cold. They move heat from a warm place, from a cooler place to a warmer place. They move heat in the opposite direction from where heat normally wants to move from warm to cold, right? So a freezer, a refrigerator, an air conditioner, they're specialized to do those things for those purposes. A heat pump basically just uses the same components, uses some nifty plumbing to turn it around, and basically extracts heat from a colder place outdoors and puts it into a warmer place indoors. And if you want, you can optimize these to produce comfortable heat for occupied buildings in cold climates that get down well below 0 Fahrenheit in the winter. And how can there be heat in 0 degree air? Well, what's absolute zero in Fahrenheit? Right? It's minus 459 is really, really, really cold. That's where you get no heat at all. Well, we don't need to worry about that. But you know, I was at Purdue just a couple of weeks ago at their biannual heat pump and air conditioning, HVAC and compressor conference. And there's people from all over the world, academic types, brilliant people, and some of them are doing some really cool research. Some of them are actually taking modeling and this novel idea of validating it with testing real stuff, which was amazing. But so many of them said the same kind of stuff, which is, you know, heat pumps are great, but you know, they just don't have enough capacity when it gets cold. They deliver uncomfortably cold air when it gets cold outside. They need backup heating source in pretty much any climate. You need to basically have a second heating system anytime you have a heat pump, which usually consists of a big electric resistance heater. And they've got such poor efficiency in cold weather, you might as well use gas. There's all kinds of different versions of this. There was a very bright guy who spoke here a couple of years ago talking about decarbonization in New York City, and he basically said the same thing. Oh, below freezing, you're going to use a bunch of electric heat, right? And I almost spoke up, but there was too many other people saying stuff, and I just figured I'd wait until I had the floor to remind people that all of these myths are absolutely true 50 years ago with the state-of-the-art technology then, and maybe 40 years ago. When I first was doing energy work, we were doing energy audits, we were doing air sealing with blower doors. We started running into houses, mostly condos in the Boston area, that had heat pumps put in because they were a cheap way to get heating and air conditioning in a small dwelling unit. And they worked like crap. All we really focused on at first was just sealing the ducts, because we were hearing about how important, you know, making ducts airtight would be. I mean, some of these were terrible. They would use building cavities as ducts, like the fireplace and chimney chase was the pathway from the return plenum to the second floor return grills, but it also was connected to the vented cathedral ceilings. So all of the return air that made it into those units was coming basically from outdoors. Really, really bad stuff. I'm not going to spend time talking about how to fix that stuff. You know, getting right-sized ductwork, designing it well, installing it well, making it airtight. Allison has done a great job with some of that stuff. Look at his website. There's a lot of good resources out there. The biggest problem with these was they did have the big electric toasters in the supply plenum, and so that kind of hid the performance problems from the people living in these places, and the bills were really, really high. So some of the rules of thumb for design, which I would say are outdated, but still a lot of people think this way. Size the unit for the cooling load in the building. You don't want to oversize for cooling because then you don't get good dehumidification. Are you actually designing for the humidity load? No, the ACA manuals have a sort of a half-baked way of dealing with that, but it doesn't really deal with it, especially for low-load buildings. But let the auxiliary heat make up the difference between what the heat pump capacity happens to be at the design condition and what the building load is at the design condition. Sometimes people design for an arbitrary balance point because they basically think the heat pump isn't worth using below a certain point. But basically always depending on a backup heating source. And so just to sort of show you what this looks like, the orange line, right, and this is in IAP, in SI units because I did this for a presentation I was doing for an international group, and so I didn't think to change the units back again. But 20 degrees C on the x-axis is room temperature. As it gets colder and colder outside, minus 10, minus 15 C. Minus 10 C is about 14 degrees Fahrenheit. So let's just say that's the design temperature for that house. The building load gets bigger as it gets colder in a pretty much linear fashion. And the blue line is the capacity of the heat pump. All heat pumps produce less heat when it gets colder outside. They also produce less cooling when it gets hotter outside, right? The bigger the temperature lift, the harder it has to work, uses more electricity, has less capacity. There's always a drop-off, no matter what kind of heat pump it is, no matter how good it is. But a conventional one has a very steep drop-off like this. And that balance point is at what outdoor temperature does the heat pump capacity dropped to a point where it crosses the building load. Below that, you have to, conventionally, you'd have to use electric resistance heat to fill in anything in that yellow triangle there. Now, for the last 20 plus years, we've had cold climate heat pumps. And cold climate heat pumps use a number of tricks, including sometimes just using a bigger compressor and derating it to provide that yellow dotted line, which is a much better, a much flatter capacity curve. As it gets colder and colder outside, the capacity doesn't drop off as much. This is great technology. This really, really helps. And as you can see, at the same design temperature, we're actually meeting the load. And we might want to put in, for that dark red triangle, just a little bit of some sort of auxiliary heat to make up just the difference for those extreme weather conditions, for those 12 hours a year that it goes below the design temperature. Depending on the project and depending on the client, that may or may not be important. So I'm going to talk a little bit about code because later on I'm talking a little more also about regulations. The International Residential Code and the IECC have references to ACA Manual J for load calculations and Manual S for sizing and selecting equipment. And Manual S, forever, when you look up heat pumps in that section, it says you need to size them for the cooling load. No more than, it gives you a little bigger margin for variable speed systems, 120% maximum of the design cooling load, and you're on your own. You got to provide some sort of electric or other auxiliary heat for the heating design condition. There's a new version, a new edition of Manual S that was published at the end of last year, beginning of this year, and it actually has provisions for the first time to size variable speed heat pumps to 100% of the heating load. Let's give a round of applause to ACA for doing that. Now, they also make it really, really complicated because I think in order to produce any kind of a standards document, ACA has to make something about as complicated as it can be. But what was interesting, I looked this up in the 2024 IRC, which isn't fully published yet because there's still some stuff going on around around sustainability and provisions that have to be moved around, which is all very political. But there's actually an exception. They do cite the new Manual S, but then it says that there's an exception for multi and variable speed that basically says as long as the design conditions are covered within the range of the equipment capacity and the manufacturer's extended performance tables, you don't need to use Manual S at all. I was like, oh, well, that's a lot simpler than going through all the things that Manual S says you have to do. So before I talk more about ratings and testing, I want to go over a couple of terms. Some of you, this is easy and old. For some of you, this is new material. I also want to say one of the reasons this is important, right? We all, Joe made the comment earlier, electrification, right? We want to shift from fossil fuels that generate carbon to electricity sources that generate less carbon, and over time, even less and less, because we can use renewables to produce that electricity. We don't really want to do it with electric heating, right? Because that's kind of expensive and kind of carbon intensive still compared with heat pumps. So coefficient of performance is just the amount of energy delivered divided by the electric input. And I'm not saying divided by the energy input. I'm saying divided by the electric input, because conservation of energy, all of the heat that goes into the building comes from somewhere, and some of it comes from outdoors for free, and you don't count that in the denominator. If you did, you would have 100%. It would always be the same amount in the numerator and the denominator. So if I have a COP of 1, that's 100% efficiency. That would be like one of those little electric heaters that you buy at Walmart, that has a 3-speed fan and sits there and goes on the table. Heat pumps typically have COPs in heating mode, depending on the conditions, anywhere from almost 2 up to 4, 4.5. And if I have a COP of 3, that means for every kilowatt hour of electricity I buy, I deliver 1 kilowatt hour of that same electric heat that I bought into the space, and I also bring in 2 more kilowatt hours of electricity from outdoors, and that gets delivered also into the house, and it doesn't cost me anything extra. I only paid for that one. So remember, in heating mode, the heat you buy at the electric meter also goes into heating. Cooling COPs tend to be higher than heating COPs, but you also have to reject the heat that you're paying for out of the structure. That has to count against you. And the reason that COPs are higher in cooling is that generally the temperature difference is a lot smaller, and so you get higher efficiencies there. All right, it's not magic. So there's 2 metrics that are used. Department of Energy specifies these metrics, and all consumer appliances and heating systems and air conditioners have those little yellow stickers on them that tell you what the standardized efficiency rating is. And utility programs and state agencies that have incentive programs and things like that, that's the number that you have to work with generally, right? So for heating, the efficiency metric is called the heating season performance factor. It's the delivered heat divided by the electric input, but it's in BTUs per watt. So it's not the same scale as a COP. It's equivalent, but if you looked at an HSPF as a number, you might have 8.5 or 9 or 10. That's 3.4 times what the seasonal COP would be, because that's the number of BTUs in a watt, right? Is 3.41. So you can kind of do a crosswalk between the 2 metrics, but it's important to remember that HSPF is a rating. It's a very specific test procedure that leads to an HSPF, and it doesn't necessarily represent how the system works in real life. And for cooling, we have a similar metric in the same units, BTUs per watt. It's called SEER. which is seasonal energy efficiency rating. I'm going to talk more about those metrics in a few minutes, but I do want to spend a couple minutes just sort of rehashing, because I just can't let go. 10 years ago, what I shared here is how I had installed 2 heat pumps in my own house. Joe made a wisecrack about me experimenting on my family. They still like the heat pumps, by the way. It's a 2,400 square foot house on 3 levels. High R values, not very good windows, not very airtight. The design load is about 20,000 BTUs per hour at 0 Fahrenheit, and I live out in the Berkshires, just over the border into Vermont, near North Adams, Massachusetts. I had 2 mini splits in the living room, just a single zone unit. Upstairs, I have a 2-zone system. The 2-zone system was not even a cold climate unit, because at that time, Fujitsu did not make a cold climate multi-zone small mini split. So there's my first floor unit. I mounted these kind of low on the wall. They work great that way for heating, by the way. But it was not my decision. That was an aesthetic decision by my wife. The second floor system, the second zone of the 2-zone system is ducted. And so there's a little air handler in the attic, which has a pile of insulation on top of that's hiding under those floorboards on the left. So not a fantastic job. But considering I added them after the house had been built, I did the best I could. Examples of what one of the outdoor units looks like. And the basic upshot of all this is I measured everything. I did an electric co-heat test in the house to see what the actual heating load was. And the measured COP was around 2.8, which is actually pretty good for the climate that I live in. Well, what's most interesting to me in a way is these units, 2012, that's like 2 or 3 generations of technology ago by the HVAC manufacturers. And so these units were only rated to work down to about +5 Fahrenheit. They are still cranking heat out when it gets below -20. And Mark, you have said this. They tend to overperform compared to their specs if you install them right. Not all of them do, but but you can't take that to the bank, right? You don't want to stake your insurance policy on assuming that they're going to overperform.
And they won't start.
Some of them,
Keep them running.
yeah. Well, and some of them do shut off when you get below a certain temperature. So DOE is actually addressing some of that stuff with some of the voluntary programs that they have right now. But basically, the best cold climate heat pumps that are out there, they have variable speed compressors and fans, which means that they can adjust the amount of mass flow going through the system and how much airflow is driving those heat exchange coils based on the load and trying to match the load. And the idea is that when the load is low, you can scale everything back and you get higher efficiencies. It doesn't actually always work that way, but that's the concept. And the concept also includes that instead of turning on and off, full capacity, nothing, full capacity, nothing, that if you're able to modulate and use lower airflows and lower refrigerant flows, that you also are managing comfort better because you don't have as big of a temperature swing in the space. So despite those myths that don't really apply to the modern cold climate heat pumps, I've also seen advocates for heat pumps in electrification overstating their efficiency fairly dramatically. And I think the simplest explanation is that they're taking the HSPF number on the box. They're looking at what's out there available. They're sort of looking at, well, what's the top quartile or so of efficiencies? Those are kind of what's being promoted in the programs. And just plopping those numbers in as if that's the efficiency we're going to get in every cold climate in the United States. And I applaud them for being advocates, but they really should be doing their homework because, an HSPF of 12 to 13 is in the range of a COP of 4. And I have yet to measure a heat pump operating in New York or New England or any similar cold climate that has an operating COP across an entire winter anywhere near 4. Well, yeah, 2.8 was mine, right? And typically 2.3, I think, would be, if you ask me, well, how efficient is a heat pump in Westford, Mass., and I had no other information other than it's a cold climate variable speed system, I'd say about 2.3 is what you can expect. Part of the reason is that not all installations are done quite properly. One of the big reasons is that the HSPF values are reported for the DOE Region 4. And the region maps for heat pump efficiencies are not the same as the IECC climates. Region 4 is a little colder, actually, than the IECC climate zone 4 that a lot of people here are familiar with, but not a lot colder. And it's not as cold as, you know, there's maybe an overlap with the warmer parts of climate zone 5, but the colder the climate, the lower the efficiency is, because you have more hours running at colder and colder temperatures, and as it gets colder outside, the heat pump is simply less efficient. So you have this weird, unintuitive thing that you can say, I have a great cold climate heat pump, but if I were to look at the HSPF rating in climate region 5, it would be lower than the heating efficiency HSPF rating in climate region 4. It's always lower in the colder climate than it is in a milder climate because it's colder. Now, the other piece is that the HSPF rating methodology is simply optimistic. That's baked into the procedure, and that's a lot of what I'm going to talk about for the next few minutes. So one more thing about the metric. They changed this it went into effect in the beginning of 2023. We now have HSPF 2 and SEER 2. But for all practical purposes, they're the same. The numbers went down on any given particular piece of equipment, and that's because they increased the static pressure requirement of the air handlers. Didn't affect ductless systems very much because they have no ducts and there's no static pressure in the test. But they previously had used a very low static pressure for a residential duct system of 0.2 inches of water, which if anyone here has ever tried to design a system that actually works at 0.2, it's not easy to do. And if you've ever looked at actual equipment in the field that HVAC contractors install, you never see it operating that low. So they increased the static pressure during the test. That made the units a little bit less efficient because they have to use more fan energy to move the heat either in or out, so that both HSPF 2 and SEER 2 numbers went down. And at the same time, the DOE minimum requirement, the NACA minimum federal standard that you have to meet in order to sell equipment, went up. And so that kind of got obscured by, the fact that the numbers went down got obscured by the fact that the requirement got a little bit more stringent. All right, but remember, these ratings are models, right? They do a bunch of tests in a lab following a very specific test procedure, and then the results of the specific tests get plugged into a model, which is a bin model. And for people who aren't familiar with a bin model, it's pretty simple. You take a climate that you want to characterize. In this case, it's region 4 for heating, that was defined decades ago by unknown provenance. And you simply assign for each group of temperatures, you assign temperature ranges 5 degrees apart. Those are the bins. And you say for each outdoor temperature, starting at 62 degrees, how many hours a year is it in that climate at that temperature? And then the next one is 57, and the next one is 52, and you keep going down, and you get a curve, right? Because there's less hours when it gets really cold, there's less hours when it's mild, and most of the heating season hours are somewhere in the middle. Okay, I don't have a graphic, but you can all picture that. So basically, you take all the test data, and you say, how do I map that test data to the performance at different outdoor temperatures? and you multiply the performance at each temperature times the capacity delivered and the energy input for each bin, and you get the total capacity for the year delivered and the total energy input for the year consumed, and the ratio of those is your HSPF. Same as what I showed you earlier with the COP. It's just in BTUs per watt instead of BTUs per BTU. There's something we have to remember here. Mr. Blasnik was the one that has reminded us numerous times, all models are wrong. Some of them are useful. The best use of the HSPF and SEER ratings for modern heat pump equipment is, I can't say it in public. The only use of them is to meet federal requirements presently. So just to give you an idea, so if you look at that orange line, that's the building load. That's very much like the building load that we talked about before. In this case, it hits 0 at 65 degrees outdoor temperature, and it gets high when it gets cold. And I put the 5 in there, even though it wasn't in the original illustration. All of those little round circles represent specific tests that have to be done on a variable speed heat pump for the heating mode tests. So there's 1, 2, 3, 4, 5, 6, 7 required tests that they have to do. And I put the one in red that says optional. That's one that's done at 5 degrees Fahrenheit. And with the new proposed rule that I'll talk about a little bit later, they're actually saying that any heat pump that says it's going to be a cold climate heat pump according to the new rule will have to test at 5 degrees. It won't be an optional test if you say that it's a cold climate heat pump. Mark is, yes, that's a good thing that they're doing that. Unfortunately, their definition of what a cold climate heat pump is different from the DOE Cold Climate Challenge, and it's different from what the NEEP database and Energy Star call cold climate heat pump. So we have yet a new definition of cold climate heat pump that doesn't actually have any efficiency requirement to go with it. It's just a capacity requirement. So just in case the market was in any way confused about what a good cold climate heat pump is or what a cold climate heat pump is, it's progress, but it's like baby steps. So somebody look at this graph and tell me, I'm trying to model the performance along that yellow-orange line, right? And I'm doing all of these tests. How many of those tests look like they're anywhere close to that line? How good do you think that trying to extrapolate and interpolate those test points to what the performance is going to be along that entire orange line, how effective do you think that's going to be? So we'll find out a little bit about it. The thing that is probably the most salient here is the first point on the bullets. All of these tests are conducted at fixed compressor speeds and fixed fan speeds. Some of those speeds are dictated specifically by the standard. Some of them have some leeway within a certain boundary based on the measured cooling capacity of the equipment in the cooling mode. And some of them, the manufacturer can choose within a fairly wide range, but they have to relate to each other, the different speeds, in a certain way. It's kind of a mess. There's something close to 80 equations that you have to use to try to fit all of that test data to the load line. And I mean, they're in pairs. A lot of them, it's power and capacity equations that are in pairs, and some of them are not about that exactly. So there's more like 30 or 35 pairs of equations that you have to use. It's kind of a mess. But it's how the standard has developed over the years. The thing about the locked test mode, it's not available unless you sign an NDA with the manufacturer. So they own the data when you do one of these AHRI tests in the lab. And so to me, the equivalent of this that everyone's familiar with is It's like the Volkswagen diesel emissions test, right? They have a test mode that depended on the car being on this test rig, and the steering wheel never moves, and that's how they know to go into test mode. The funny thing is in Europe, they all violated the standard there as well, except that the standard had built in an exception to preserve the life of the engine, which means they turn it off all the time because they know it kills the engine life. They turn off the emissions. And in the US, what got Volkswagen in trouble was they lied about it and tried to hide it. That was the only problem. Now here, with heat pumps, it's a requirement by federal regulation that you've got to do it this way. It's a test mode and has nothing to do with how the system actually operates in real life. So starting around 10 years ago, I got involved in this while I still was working with CSG. Some people in Canada and including a couple of West Coast utilities and groups from the US were getting interested in load-based testing and rating of heat pumps as an alternative because they were recognizing that HSPF did not really do a good job of describing performance. Interesting enough, over the last few years, I have gotten involved with a couple of committees and working groups with the IEA and with the ISO, and there are quite a few other research institutes and government agencies around the world that are working on load-based testing of heat pumps, and we're collaborating, which is great. You know, some of the biggest research that I'm aware of is happening in Germany and Japan and in India. And in India, they're also focused on high performance for the global south, which is massive dehumidification needs and cooling, you know, is really the primary driver. So the Canadian Standards Association is housing this project that I've been working on basically for the last 10 years. And starting in 2019, we published this first version of this test procedure. It was called EXP07. And then after an extensive public comment period and some rewriting, it got re-released, but we couldn't call it EXP07 anymore, so it's now SPE07. I don't understand CSA's naming convention. There are a bunch of Canadians, so who knows? So the concept here is we're applying a virtual building load in the test lab and using the system's native built-in controls. It's whatever its algorithms are for trying to maintain comfort in the space, and all of the testing is done that way. So how does that work? You know, here we got the orange line, and you can see the purple dots. And when it's mild, it always matches. And it's at a certain point, if you look at the purple diagonal dotted line, that's sort of an imaginary equipment capacity curve. At a certain point, it gets too cold, and the equipment capacity doesn't meet the building load line, and then you simply do a full load test. Then you fix the indoor room conditions, and you just let it run at its full output, so you can still measure how it performs when the load is too large. And so it's big difference from the DOE test. And so how this works in the laboratory, typically on the left is one psychrometric chamber. So there's mechanical equipment in that the duct that runs outside the room, that is there to maintain particular temperature and humidity conditions in the chamber. And a similar thing, the outdoor room is on the right, and that also has reconditioning equipment that manages the conditions in the chamber. And in a typical fixed speed test, this is what you get. You get two psychrometric chambers, and the indoor conditions are just fixed, and the outdoor conditions are fixed, and they run it in the test mode, and they see what happens with the equipment, which is usually not a surprise, because they know how it's going to run. With the load-based test, what you're doing is this little dotted line. You're measuring the heating or cooling capacity of the equipment in real time as it's running. And you're basically saying, well, I'm going to create a model of a simple version of a building that has energy coming in and energy, you know, in or out through the enclosure, and you're trying to match that with the opposite sign energy of the equipment providing cooling or heating. In this case, it's showing cooling. And that gets programmed into the equipment room controls, the test room controls. The outdoor room is held constant at one condition, and the load that you put on the indoor unit, on the indoor room, varies depending on how cold or how hot it is outside. So when you're testing really cold outdoor temperatures and heating, you give it a bigger load. And when you're testing mild temperatures, you give it a smaller load. That make sense? Yes?
Does the heat capacity of the indoor room get adjusted to match the heat capacity of a typical house? So that
You mean the thermal mass?
Well, yes.
There's a separate term in the virtual building model for shallow mass, and it's different from the thermal mass that we were talking about earlier, because we don't care what the time constant is for hours. What we care about is the cycling of the thermostat, and so that stuff has been measured, and we've got an estimate of that that's baked into the model, and the size of the load is scaled to the size of the equipment you're testing. So that if you're testing a little heat pump, the loads are smaller, and if you're testing a big heat pump, the load line is steeper, but it's always scaled to the size of the heat pump based on the size of the house you would expect that heat pump to be installed in. In cooling mode, there's also a virtual building model for humidity. So instead of holding it at a specific wet bulb temperature inside, you actually let it manage the humidity in the space. And all this is done in real time on a 10-second basis, and you let the thing run for anywhere from an hour to up to maybe 4 hours, depending on how the unit is behaving. There's a whole set of rules to how you decide, okay, now I've got a stable enough answer over time that I'm going to wrap up that test and go on to a new test condition. And so we've got 5 test conditions in cooling and 6 or 7 in heating, depending on the unit. And we get a whole bunch of test results, but the test results are lined up along that load line, and they include stuff like cycling and defrost that are separately accounted for in the DOE procedure mathematically, but not really in a real-life kind of way. One of the things that we found fairly early on is that thermostat placement in the indoor room mattered, and it was really hard to figure out the best way to sort of handle that. And so basically, the Purdue folks that did a lot of this research that was funded by the Northwest Energy Efficiency Alliance and PG&E and some other folks that were involved in this process, they developed a chamber that you put inside that indoor room that is finely tuned to match the control point of the indoor room, and has a consistent air velocity moving across the thermostat sensor or the control. That it's based on an ACMA test that is a standard thermostat test procedure. Is it right? I don't know, but is it consistent? Way more consistent, yes. And so all this stuff has kind of been tuned to both represent buildings reasonably well, but also to be testable and reasonably repeatable, and not to have to spend too many hours for things to stabilize until you can get a reading and move on to the next test. So an example of a cooling test sequence, if you look at the bottom graph first, the reddish line is the outdoor temperature, and you can see that's moving up in stages. So we go from 77 degrees up to 113 degrees, 112 or 113 degrees. Each one of those horizontal lines is one test condition. And then the blue that's a sawtooth going up and down, that's the indoor room temperature. So in the first couple of test conditions, if you look at the upper graph, you can see the compressor is turning on and off. The blue line is the total power, and the green is the cooling rate, and you can see them both going on and off together because the load is so small that it's cycling. That unit variable speed systems don't vary down to almost zero. They have a certain limit, and below that limit, if you have a smaller load that you're trying to meet, there's going to be some temperature change down, and the unit will respond in this case, as the room temperature gets warmer, it will turn on. And so you can actually see that this is behaving like a real unit would in a real room. And as the load goes up, when you get to the third segment here, you can see that it's still hunting up and down, but it's not turning off. So it's now modulating and trying to meet the building load and modulating. In the second to last segment, you can see it's still modulating, but it's pretty close to the very top of its input power and its capacity. And at the 113-degree point, there's nothing here that shows this, but that was converted to a full load test, and that's just the maximum capacity that it can produce. All right, I'm not going to spend more time on how that works, but that's the sort of the technical stuff of how the test process works. And then basically we take the results of all of the lab data tests and we map them to 8 different climate models in the US and Canada. And those climates are kind of similar by design to the IECC climate zones. There's dry and humid, which only really affects the summer bin models, and it goes from Gulf Coast or the hot dry in the Southwest all the way up to subarctic, which is lots of Alaska and northern Canada. So what we've learned from doing these load-based tests, we tested about 22 heat pumps over a period of 3 years, and not surprisingly, the results we got, which are on the right, are different from the AHRI ratings of these same units. On the right is the HSPF scale. These were all done before HSPF 2. On the left is the COP scale, but they are aligned, right? If the performance was the same, it would be a horizontal line. So 2 things that I notice here. One is that it's not flat, that SPE07 test generally yields lower efficiencies, seasonal efficiencies than the AHRI test. And second of all, it's inconsistent. And on the heating side, the best way to show this was that we've circled 5 of the units had the exact same HSPF rating. And look how different they were when we tested them under load in the lab. All right, from the worst to almost the best. And make a note of that one that's on the very bottom, because it's a little bit of an outlier, and it was not a test error. One of the first things manufacturers do is they say, well, that's the published HSPF. We didn't base that on the same unit that you tested. And we often put a little margin of safety when we publish the HSPF, because there's audit tests. And we want to make sure, because so sometimes the HSPF is underreported. I'm like, underreported, yeah, but this is going the other way. But it was a legitimate point. We didn't test these units using the AHRI test. We tested them and then compared them to the AHRI rating. On the cooling side, the SEER ratings were all over the place. There were none that matched, or only maybe one pair that matched. But you can see the rank order is really different, right? Also, the overall difference is bigger, suggesting that maybe SEER is even more optimistic, overly optimistic than HSPF. But again, we don't know. Is our test method actually better? We don't know. One of the best AHRI rated, the very best unit on the AHRI scale was actually one of the worst ones that we tested. So one of the things you notice when you start doing this load-based testing is the equipment can act weird. And in this case, we got 3 cooling mode tests, and you can see that in the first 2, it's modulating and cycling, but it's never shutting off. When it gets to the higher load in that third segment, it actually runs at a higher rate, and then it shuts off. Does that make any sense for a sort of normal variable speed system? You would think once it has the capacity to meet the load that there'd be no reason for it to shut off. So remember that one HSPF that was way, way, way down low on the right-hand side? That manufacturer, we shared a lot of this data individually with the manufacturers. Otherwise, it was all anonymized. But for each of the manufacturers that we talked to, we were willing to share. This one was yours, right? So they can learn from it. And this manufacturer found it was pretty interesting that their system really sucked. And they came back to Christopher Diamond at NIA a year or two later, and they said, oh, we have a new product that's in the same product line. It's got a new model number, new AHRI rating, but we'd like you to test that one in the lab as well and see how it does. And so these pairs of lines are the two units, okay? And the crosshatch lines are the old unit, and the solid lines are the new unit. In heating mode, in the first pair there, you can see the HSPF rating went up by 8%. So they did make some changes in the hardware that improved the performance during, using the normal test. The SEER, which is the third pair there, also improved by 8%. Amazing how consistent that was. When we tested it in the lab, the heating performance using the load-based test improved by almost 60%. And on the cooling, it improved by 80%. It's still a lot worse than the AHRI rating, but it doubled the amount of cooling that it could produce for the amount of energy. And the simple explanation for this is cycling. This thing, when we looked at the graphs of the old unit, in every test condition, it was cycling on and off all the time, under all the load conditions. It was acting like a single speed unit. So you got none of the benefit of all of that fancy stuff that they built into the box. So you can see the same exact test conditions here. The one on the left is cycling on almost 800 watts. It tries to modulate down, it goes up, it settles on 500 watts for a bit and shuts off. And then rinse and repeat. On the right-hand side, same indoor and outdoor conditions. The thing is running, goes up, it's off, it runs, it goes up to about 400 watts, drops down to under 300, sits there for a while. All right, it's gotten too cool in this space, and it finally shuts off. I will observe that there's a bigger hysteresis of that thermostat, significantly bigger. But they both met the requirements of the indoor room control that we set in the test procedure. All they did was change the firmware, and they got a 60% improvement in the heating efficiency.
Bruce, is this just, they just didn't do it properly the first time? Someone on the firmware side just didn't do it?
Is this just that they screwed up?
Yeah.
Yeah, basically. Yeah. No, it wasn't just the deadband. There were other issues with it.
I may have missed a comment you made, but was their correction influenced by feedback that you got?
Was the correction influenced by the fact that they knew that they had done so badly the first time? One can only conjecture. I would say the likelihood is very high.
Are you being modest?
I don't actually have personal insight into the answer for that, but based on comments from Christopher, I would say they knew that there was a problem. Okay, so I got 20 minutes or so. So our conclusion is EXP-07 is very different rank order than the AHRI test. Suggests that HSPF and SEER are poor indicators. And there's been plenty of field studies that also indicate HSPF and SEER are not very good metrics to describe efficiency. Why does this matter? Because there's money being put out to people, contractors and homeowners, to put in high efficiency stuff. And if this is the metric we have to determine what's high efficiency, duh, it should be right. And load-based testing appears. One person brought up the question, well, what if people game the equipment controls so that it does better in load-based testing? And the answer is, I hope they do, because if they do, then it should perform better in real life as well. So I've got to pick up the pace just a little bit, but there are a couple of reports that show some of the data I've been showing you in much more detail, mostly on the NIA website, but also a paper that we had shared 2 years ago at the Herrick conference. And all the PDF of this will be out for everybody later. So is load-based testing really better? We wanted to answer some of the naysayers that were saying, well, you're just comparing it to the published rating. That's useless. So the concept of repeatability, reproducibility, and representativeness, lab tests understandably want to be constructed in such a way that they're repeatable, so you get similar results every time you run them. Reproducibility means that you also get similar results when you run them in one lab versus a different lab versus a different lab. I think it's pretty self-evident why all that stuff is important when you have a test procedure that someone is going to be checking up on you at random with some of your equipment. It's the representativeness. As far as I know, nobody ever did any studies to show that the original HSPF and SEER were representative of how equipment operates. So we set out to do that a couple of years ago. Reproducibility was looked at, wasn't great with EXPS7. The repeatability was pretty good. And the reproducibility, it wasn't really a surprise that didn't do well because we only had 2 labs that tested, I think, 5 different machines. And one of the labs wasn't really up to speed on the load-based testing. It's a novel approach, and lab people, they didn't all read the standard exactly the same way. So we did a lot of improvements to try to fix those interpretation problems. And then starting in 2022, we decided we're going to actually test some units in the field and then take the same exact boxes and bring them in the lab and test them using load-based and fixed-speed testing. So the basic idea is we're going to test the test methods. We're not going to see how the equipment performs. We don't really care. We just want to see how does it perform in the field versus how the 2 different lab tests predict the performance. So we got 3 mobile homes in Lincoln, Nebraska. They're sited, the same orientation, they're brand new, right from the factory. We rented all 3 of them for a year. And each one has a ducted system and a ductless system. So you can see that in the back there. There's 2 outdoor units, one for the ducted and one for the ductless. And we did a flip-flop test where each week one of the systems ran about half the week and then the other one would run. And then we just switch back and forth for the summer and switch back and forth for the winter. I'm not going to go into detail about this, but we did go to some trouble to measure the thermal load for heating. You can't really do that for cooling, but we weren't too far off because we'd seen electric bills from the neighbors. And we did a co-heat test a couple of nights to measure the UA of the buildings, and did cycling tests with the native built. The 15 kilowatt furnace in these units was the electric furnace that shipped with these. So they were about 3 times the size they needed to be. But we got load curves and cycling rates and figured out that the loads were a little small. So we changed some of the windows for sheet steel and added some drywall to get a little more shallow thermal mass, because these were completely empty houses, and that all made sense. David Ewell from University of Nebraska was really instrumental in this, and especially, he was the one that insisted that we've got to have refrigerant mass flow meters in every unit, and that saved our butts. There was some issues because, of course, when you add stuff, you're adding a little bit of resistance, you're adding more refrigerant volume, it's gonna change the performance. Yes, it is, not very much. And we shipped these to the lab with the same piping and everything, and so it was installed in the lab in the exact same conditions that we ran it in the field. Field measurements of airside capacities of heat pumps and air conditioners is fraught, and especially in air conditioning mode. And I'll have a slide of that in a second. This one is the load lines, and we wanted to measure the load lines as they were operating so that we could replicate those in the lab with the load-based testing. We didn't want to just use the standardized load lines. We wanted to say, we're not trying to say, did we pick the right load lines? Because these are real houses, and the relationship between the heating loads and the cooling loads are not going to match what our typical house load lines that are built into the test procedure. And so we're going to do the test in the lab based on the load lines the loads that were really seen in the field. And of course, it's not a line, it's a big bunch of scatter, but it still fits the line pretty well. On the measurement side, the blue trace is the refrigerant mass flow meters for a particular period of time of a few hours, and the red is the air side measurements. On the cooling measurements, the air side were consistently low by between 10 and 20%. And we're not really sure exactly why, but it's probably the delay time of the humidity sensors. It's really hard to get accurate humidity sensors that are also fast. And when you're measuring stuff dynamically, that matters. So what they did is, well, we couldn't actually trust the refrigerant measurements all the time, because sometimes it's liquid or gas going through that pipe, and sometimes it's two-phase, and when it's two-phase, those measurements aren't good. But we know whether it's two-phase based on some of the other sensors, and so the team at UNL actually was able to say, we'll get a fit between the air side measurements and the refrigerant side measurements, and for all of those minutes that we don't have good refrigerant measurements, we'll use that curve fit to backfill what the proper capacity was. And I think they did a pretty good job of that. So, what happened? Well, this is all 5 units. There were 6, if anyone was paying attention. One of them had multiple problems, and we decided to throw out all of the data and not try to figure out what data we could use and what we couldn't. So A, B, C, D, F are the 5 units. Left side is heating, and the light colored green is the field COP, which we have normalized to the same. We split the field performance into bins, and we basically ran it to the same cold, dry climate that we use for the comparison between the load-based test and the AHRI test. So we're normalizing everything to what it would have performed in a standard climate so that we can compare them. And the load-based test is the solid lines, and you know, they're more a little high than not. There's one that's a little low. On the cooling side, the load-based test pretty consistently a bit low on predicting the efficiency. That might explain some of the big difference between the ratings and SEER and the load-based testing and cooling. I don't know. There's still some question marks there. On the heating, all right, I'm sorry. On the AHRI side, we had a lot more over-prediction. The solid lines are the AHRI test, and a lot more optimism about heating efficiency. The one that actually performed the worst in the field had the highest result from the AHRI test in the lab. And similarly for cooling, some of them were pretty darn close, and some of them were very optimistic. So there's a visual of the actual 5 points. The middle is the field. And so you can see on heating side on the left, you know, we're measuring in generally SPE07 on the right is, you know, on the left graph is cooling. I reversed, I apologize. I should have put heating on the left, but yeah, so M1, which is the AHRI test, a few predicted really high, and more or less, there's a little more parity there with both of the tests. SPE07 tends to be a little on the low side. For heating, there's more parity between the field and SPE07, and more over prediction with M1. I got 10 more minutes. I think I can do this. So looking at this statistically, it's a pretty small sample. I wouldn't really read a lot into the ducted versus ductless because there's only 2 and 3 of each, but it is a pretty dramatic difference. But basically, when you look at all 5 of them, the mean absolute percent error on the lower right there, for cooling, it's 13% for SPE07 and 22% for M1. So we're closer by a fairly large margin, but I wouldn't say it's as dramatic as I would have expected. For heating, it's a bigger difference, 10% mean absolute error on the load-based test and 36% on the standard test. Just to sort of give this a bit of a policy context, in January 2023, DOE issued a request for information related to a proposed rule, and they included quite a few questions about load-based testing. And I found this very interesting. They really took the work that we had been doing seriously, but this was before any of what I just shared with you was published about the field testing. And I'll give the spoiler first. They basically, in their more recent notice of proposed rulemaking that came out about a year later, this February, they basically parsed through all of that and the various answers they got to the RFI, and they said, you know, we think load-based testing is promising, but it's not ready for prime time to actually create a rating based on load-based testing because of a bunch of reasons, and they were all reasonable reasons. And I thought they did a good job giving it a shot and considering it and deciding that, no, it's not actually ready for prime time yet. At the same time, a few months after they did this RFI, they got with AHRI and they basically said, if you can write 2 new versions of the test procedure by the end of the summer, we will adopt them by reference into the regulation, which is kind of stunning on 2 counts. One is how do you do a major update to a published standard like that in just 5 months? And number 2, you know, that previously the DOE has published their own version because there's always some differences between what they want and what AHRI has published. And I started going to those meetings and I became a voting member of the STC. And I was stunned, number 1, by the amount of collaboration in the room and the fact that there was not a lot of fighting between the manufacturers and the advocates. Quite a few of the manufacturers have actually been very supportive of the load-based testing. And it was a huge collaborative effort. We didn't get everything we wanted. We wanted to get better indoor conditions for cooling tests. You know that 8067? Who can tell me where 8067 came from? 80 dry bulb, 67 wet bulb.
Joe Stephen made it up?
You know, a lot of people think, oh, it's because the ducts are in the attic or because this. Actually, that number goes way back to the early 1930s and has been consistent for testing air conditioners ever since. And basically the reason was people's expectation for indoor comfort were not that extreme. Any cooling was better than what they had. And most mechanical cooling actually in those early days was done for warehouses and process facilities and not for human comfort. And 8067 has just stuck around ever since. Anyway, so we did it. We came up with 2 drafts by the end of August. And thank you. I can't take credit for that, but I participated in it, and it was I have heard so many nightmares about public process like that going badly, and I'm really glad I never had to actually be in the room when that was happening, because it didn't happen this time. The quick version is the short-term 210, 240 standard is harmonized with Appendix M1, so it can now be adopted by reference, but it includes a few things that are really interesting. The longer term, it has been changed to AHRI 1600, and they've changed the name of the metric because they're going to include standby energy in the seasonal calculations, and a bunch of other mostly small tweaks. I will not get into them now. But what was the most interesting to me is this thing they're calling a controls verification process, which is now going to be in the short term, according to the proposed rulemaking that came out, but it's not going to be a required test. This is introduced for enforcement. And the reason is they don't want to change the metric or the federal requirements in this next round, and they haven't done that because they're not requiring this test. But you know, if the manufacturers know that this could be done as enforcement, they're going to do it on their own.
What is that?
Good question, Andy. What is that? So basically this is, actually I'm going to show you, the thermostat set point is set to 80 degrees Fahrenheit. Unit operates under its own controls. This is the load-based test. But instead of doing it at certain points and creating a rating out of it, what they're doing is they're starting at full load and cooling at 95 degrees, and they're running it long enough to say, all right, we're pretty close to the rating point at 95 within a tolerance, and we're confident that the thing can operate at the capacity that they say in the fixed speed test under its own native controls. It ramps down, there's an intermediate test, and there's a statistical thing that gets applied to the performance over a period of anywhere from an hour and a half to 3 hours, and up to 6. What that is to do is to make sure that the unit is not acting like a single speed unit, which we found, right? There's a certain way that they're going to demonstrate that this is actually a variable speed system, and the test lab can decide within a range what that load is going to be. So they can't game it to just work right at one particular load in the middle. And then they do it again at the low load at the low temperature difference. So they're doing the two corners, high load, high temperature, low load, low temperature, and they're checking for modulation in the middle. Hang on. And then we're doing the same thing with heating. That equation came from our standard. Lou.
Want to make sure I understand it. So the point is these aren't separate test points. This is a single test under what amounts to a dynamically changing.
Well, it's a single test, but it includes 3 steady state points
right.
that are part of the specific conditions.
And
no.
then set up again
No.
at the new test condition.
That's right.
Stop, set up, no.
This is one test that's run in a lab,
those points.
and you're moving between those points over time,
different situation.
but you're getting 3 different results that you're using to corroborate
Right.
the regulatory test.
Right.
Same equation, a slightly different form to suit what they're doing. This is a huge win.
Oh, yeah.
This is a big step forward. And the same thing being done in heating. At low temperature, it'll be 5 degrees if they're required to do the 5-degree test. It'll be 17 if they're not calling it a cold climate heat pump. And they'll do high load, low load, and a plateau in between. So we're calling it the 4 corners. High and low on heating, high and low on cooling, as well as checking that it's actually variable speed. I got a couple more minutes? One. All right. But you said. We need to dig into the data a bit to see if we can learn some more things. We ran out of budget, so there's some analysis that we could do. We did do some repeatability tests in the lab, and we found, big surprise, it's still good, even after we changed the standard. The reproducibility we're looking at now, which is only 2 of those same units, but they're being tested starting the beginning of this week in a lab in Canada that's a different lab than the one that did all this stuff for us. And some of the most interesting things I'm looking at now using load-based testing is really homing in on low-speed performance in heating mode, which is at that 47-degree outdoor temperature, and really trying to home in on understanding better how different machines work. We're testing 6 units in the lab at UL starting a few weeks ago, and we'll be wrapping that up soon. So keep your eye over time on the NIA website. This thing about be careful what you say came back to me a few weeks ago. I got an email from somebody at ABCD saying, I want to talk to you about heat pumps. And I was like, oh shit, I told him some stuff a couple of years ago, and now he's gotten in trouble. And as it turns out, basically he said, I did all the stuff, we've been doing all the stuff that you said we should do, and everything's been working really, really well. And here's the stuff. You can read it if you have questions. Do we have time for a few questions? Yeah. Great. Kimberly's first.
Words. Electricity.
And waves.
Hi, Kimberly Llewellyn, Mitsubishi Electric. First of all, Bruce, I just want to thank you for this really important work that you're doing. One thing that I'm not sure everybody understands is that our standardized tests are super important, right? Because this is what prevents manufacturers from making whatever claims they want, so that we create a standardized test that everybody's having to play by the same rules. But it's also the case that the test standards, as you've so masterfully described, are wildly inadequate for current equipment. And people don't understand always that the manufacturers are designing to the test. And so that actually creates limitations within the native controls and also the general operation of systems that are sometimes capable of doing much better. So I am really grateful to you, speaking, on behalf of manufacturers, for doing this work.
Yes.
Thank you.
Thank you.
Yeah.
And I can't really take credit. I'm just there to hold people's hands and make sure they're talking to each other, and I wrote a bunch of this stuff. But there's huge support from PG&E, NIA, the Canadian government, BC Hydro, and lots of manufacturers over time. So thank you to all of them.
But you're being modest.
Thank you.
Okay, this next thing, really quickly, I'm sorry. This is also really important. I'm not sure I should say this next thing, but because it's going to sound like I'm tooting my own horn. And if nobody toots your horn, eventually you're going to need to toot it at some point, right, yourself? So ACA Manual S, those new heat pump, variable speed heat pump sizing guidelines I wrote. And again, with the collaboration of a working group, some of the people who collaborated are in this room, David Trelevin, Alex Meany, I don't know if Wes Davis is also here. The reason that I am saying this is not to toot my own horn, but to accept responsibility. Should you find in practice that that's actually not, that there are issues with that. And you'll find implications of sizing your heat pumps to your peak heating loads. And there are implications on the cooling load side. So that's a subject for another talk. But I won't, that complexity that you said is important. Like, let's remember that it's important in that context too.
And
thank you.
And for all due credit, that Manual S version is another huge step forward, and I'm applauding it. So thank you, Kimberly. It didn't quite come out the way I meant it to when I said that. Yeah.
Thank you, Ben. Thank you for all the work you're doing. I'm very, very interested in the load-based ratings for sensible heat factor at different loads.
Yeah.
Especially low loads.
So basically what we did is there's the humid and the dry, and so for humid we set lower indoor set points and an SHR of 0.8. And then for the dry, we went from an SHR of 1 to actually an SHR of 0.95 based on public comments, and the indoor temperature set point is a little bit higher in the dry climate rating. But there's no, the equipment isn't trying to control for humidity, so we just report what the humidity was at the different test points as part of what gets published when you do one of these tests.
Okay, can we get a test point down at like 0.6, I'd say, John?
You can do that in the lab. We haven't, but yeah, we tried to balance practicality and sort of overall performance. But yeah, no, that's a good idea. Thank you.
Hi, Graham Wright from FIAS. I think I have a similar question. I was listening to this, trying to figure out, okay, does this still work for passive houses, for low load buildings? And it sounds like kind of overall you've sort of normalized to that. Probably the overall longer time constant probably doesn't matter, but I did wonder about the relatively high latent load. Whether
the load line is still a pretty typical house.
Okay.
And one of the problems is even with the variable speed systems, people think, oh, they're variable speed, so it doesn't matter how you size them. But for any really, really low load buildings, all this stuff just gets amplified and magnified, and the rating is not going to apply, ever.
Okay.
So I think you need good design that understands the low
Stop
load
building
building.
such a good freaking house, Graham. Roger that. Thank you, thank you, thank you. Okay, we got a break, 21 minutes, let's roll.